Good morning. We are ready for our first midterm. So we've covered chapters 1 through 4, and we want to today do a bit of a review, look at some problems, some questions that have shown up on previous midterms from previous years. And so what I did is I printed this out. This is an example of what a midterm looked like from a few years back, and I've got two of these. So let's go ahead and take a look at these questions. Now I do want to point this out in advance. These questions are very useful to look at, and they give you kind of a feel for the format of the midterm. So for example, there's 4 questions, 1, 2, 3, 4. We will have the same. And then for each of the questions, there's individual A, B, C, Ds going on. Each of the questions are evenly weighted. So, out of 100 points, each of these are 25. And then typically, if I have A, B, C, D, E, those get, for the most part, evenly weighted also within the individual problem. So something to keep in mind as you're looking through this exam. So this is the format. Now, of course, the midterm is going to cover all of chapters 1, 2, 3, and 4. Don't focus just on these problems. So there's 4 problems here. There's an additional midterm that we'll take a look at after this. We'll do these 4 problems. If you guys want to take a break, that's fine. I think I'm just going to go straight through, but you can always put this on pause. But I'm going to do one set of problems, and then we'll come and go right into a second set of problems. So let's go ahead and get started and see what this looks like. So on this first problem, this is coming from chapter 2. Now remember that chapter 1 has useful things in it, but it has more general items. So it's looking at units conversion, it's looking at units themselves, keeping track of significant figures. They're important items, but there's not going to be any problems on the midterm that specifically come from chapter 1. So I'm thinking in terms of chapter 2, 3, and 4, and maybe a little more heavily weighted towards 4. So on this problem, on this set of problems, for example, if we take a look, this is kind of one-dimensional kinematics. That's coming from chapter 2. 2 would fit in with chapter 3, two-dimensional kinematics, and then 3 or 4 coming from chapter 4, and that's what I would plan on. The nice feature about a chapter 4 problem is you can include everything, all the concepts from 2 and 3, and include it into one problem, kind of covering everything we've looked at so far. And for better or worse, that's the way physics works, is everything will continue to build through the semester. All right, problem 1, we've got a rocket. It rises vertically from rest. So it's going to start off on the launch pad, I guess, and then it says that we're going to have an upward acceleration of 27 meters per second, and that lasts for 15 seconds, and then the fuel's depleted. And so now they're not telling us the mass of the rocket. They're not asking us to calculate different forces. They just flat out tell us what the acceleration is. So again, this is a pure kinematics problem. And so what I did was I said, okay, the rocket's going to launch, and then for 15 seconds, it is going to have an acceleration of 27 meters per second squared in the upwards direction. Now once the fuel runs out, the thrust is gone, then the accelerations will be purely due to gravity. Now gravity was taking place during the first part, but they haven't told us the details of the forces. They've just told us the net effect. So we don't have to add or subtract gravity in that first part, the gravitational acceleration. So if you think of this as 3 different, breaking the problem up into 3 different time segments, and then stating what the acceleration is in each one of those, that's maybe a good way to kind of organize how we're going to be looking at the problem. Now the first part of the problem says how fast is the rocket traveling at the time it runs out of fuel. So that would be at point B. Now we've got formulas. This is all going to be constant acceleration, because when we look at the different segments of the problem, the accelerations are constant during each of those segments. So let's just pull out all of our equations for constant acceleration. And for problem A, I said, hey, I'm starting from rest at point A. By the time I get to point B, the speed should be whatever the acceleration was during that time interval times the amount of time that went by. That's 27 meters per second squared. And that acceleration lasts for 15 seconds. So that's a good example of just, a very standard constant acceleration calculation. It says that at the end of the 15 seconds, the rocket's going 405 meters per second. That's like 1,000 miles an hour or something. So it's going at a pretty good speed here. All right, so that's how fast it's going. Now, how much distance have we traveled? Now, again, this is a constant acceleration formula. I have left off x naught because I'm just going to call that 0. I left off v naught because we start from rest. So the only term left is the 1/2 at squared. And that leaves us with, 27 meters per second squared times t squared times a half. That's 3,040 meters. Maybe 10,000 feet. This thing has risen during that 15 seconds. That's a pretty good climb. In part C, it says, what is the highest height? Now, here I have to start thinking of combining different segments of this problem. We already know that by the time we get to point B, we have risen to a height of 3,040 meters. Now, there's a couple different approaches here. What we could do, what I chose to do here, is I first of all looked at the time. So I went back and I did it in 2 steps instead of in terms of 1. I went back and looked at the time, and I specifically wanted to find out how much time it would take to get from point B to point C. We already know from A to B is 15 seconds. So I isolated that part of the process and said the velocity at C is whatever the velocity is at B minus the acceleration times time. Now, I wrote that as minus gt. The acceleration has reverse directions. So, as always, pay attention to signs. Make sure that the pluses and minuses you're putting in the formulas accurately represent what's going on physically. So I'm just going to go ahead. G is 9.80. G itself is a positive number. I'm going to put a minus sign in by hand here. And then set this equal to 0. I know at the highest point, the velocity now is 0. So hey, VC can be set equal to 0. And that says, solving for the time, it's going to be VB over G. It says that it's going to continue upwards. It's going to be slowing down, but it's going to continue upwards for an additional 41.3 seconds. So now that I have that time, and I'm keeping extra significant figures in my calculator. I don't know if that's necessarily required, but that's certainly some way to avoid round off. So in the background, I'm keeping an extra sig figure too. Let's see. So I can take this amount of time and put that back into my displacement formula. Now here, there's a handy way to bring HB into this, so I went ahead and did that. I said we're already starting at a certain height, 3,040 meters, and then I put in the velocity at B. That would be my starting velocity times time, and then the acceleration term again is getting subtracted off. It's not picking up speed in the upwards direction. The acceleration is downwards. So that says that it actually, while the rocket was accelerating upwards, 3,040 meters, but look how much farther it was able to effectively coast once it had run out of fuel. So yeah, we're starting right off with rocket science here for our first example, and this is going to reach an altitude of 11,410 meters. If you find discrepancies in these numbers, if you find I have errors in here, let me know right away. I double check, but you know. So in part D, it says, now what happens on the way back down? So the rocket's going to reach that height and then it's just going to drop right back. We're treating this all as a one-dimensional problem. So we're saying that it accelerates vertically upwards and then it just falls vertically back downwards. So for this, what we could do is we could bring in another one of the constant acceleration problems. We can say that the speed at point D squared would equal the speed at point C squared plus 2GHC. So the height at point D is 0. That's not shown. We've got that written down here. Oh, we don't have it. So the height at D is 0. The speed at the top is 0. And so that drops out. And it says that I can calculate the speed just by knowing the gravitational acceleration and the distance that it's going to drop. And again, these are formulas of constant acceleration. Now, it's always good, you know, I'm always encouraging students, don't just plug numbers into formulas mindlessly. As best you can, think about what the formulas are telling you. So, you know, the speed by the time the rocket impacts depends on the gravitational acceleration and the height. And stop and think, yeah, that makes sense, right? If I'm dropping from a higher height, that would be a higher speed. If there's a larger gravitational acceleration, that would create a higher speed also. So maybe we're on a different planet. All right, plugging the numbers in, I ended up with 473 meters per second. So if we neglect air resistance, which is probably not going to be a good approximation, but that's what we do. So far we're neglecting air resistance. It's going to impact at 1,000 meters per second. It's going to be going, to probably better than 2,000 meters per second when it hits, because it's falling from a really high height. And finally, part E, it says what's the total time. Now, as we went through this, we were given how much time it took to get from point A to point B. And then we had calculated in an earlier step the time from B to C, so 2 of those steps are taken care of. What we could do, since we know these times already, we just need to get that last one. How much time is it going to take to come back down? Now, I think it's going to take less time more time to come back down than that's questionable too. We'll have to see. I was going to say there's a way to kind of reason through how long it might take, but I don't know if that works. So on the way back down, we are going to, so back down to here would take the same amount of time as going up. Here, yeah, we're going faster. So this is going to take a shorter amount of time. So coming back down should take a shorter amount of time, I think, because we're going faster during that segment. So in any case, I'm just treating it as C to D and saying that dropping that distance is given by 1/2 gt squared, and then we can solve for t. Solving for t here says it's an additional 48 seconds. How long did it take to go? Yeah, so this is 15. So yeah, so it's a shorter amount of time because we're going faster. So adding all 3 of those times together, 104.5 seconds. So it's less than 2 minutes. So the 15 seconds, it got to point B, another 40 seconds and it got to the top, and then another 50 seconds and it impacts on the surface. Okay, questions on any of those items in problem 1? Okay, so this is, I think this is a level of difficulty for problems on the midterm. I think this is probably kind of a typical amount of difference. Some of these are a little easier, some are a little harder. This one leans to be just a bit more challenging, but still. This one too, I think, is coming in, right around average, maybe a little bit on the easier side. I noticed here I could have asked additional questions, so be prepared maybe for a couple more things getting asked on a problem like this. Anyway, this is projectile motion. So projectile motion definitely is something that could show up on the midterm. It's such a good example of two-dimensional constant acceleration type problems. With constant acceleration in the vertical direction and constant velocity in the horizontal direction. And again, these are approximations assuming no air resistance. So it says that this time it's a baseball hit at 40 degrees angled. Speed of 35 meters per second, and it's a meter above the ground. So, that makes sense, right? So, a meter above the ground, the ball gets hit, and from that point, so I'm going to call that point A, and I don't know how, for me, these diagrams, and I should just say this too, that in many of these problems, it's going to come out and say, draw a diagram. So that could have been one of the parts on this problem, is draw a diagram of what's going on. I should have put that in. I could easily put that in, because I always feel like unless you guys can show me, you can draw a picture. If someone says, well, yeah, draw a picture of what you're describing here. If you can't do that, you're not really understanding the problem. So I always want to see diagrams versus just numbers plugged into formulas. All right, so here's the diagram. Point A, and then point B is at the very top, and they ask something about that. And then point C is where it would land. Now, I think I ended up adding point D right here. I didn't label it, but I went back and point D at a distance 120 meters out turns out to be important too. Let's take a look and see. Part A is saying, what's the maximum height reached by the baseball? So for this, again, I'm bringing out constant acceleration formulas for the vertical motion. In the vertical direction, it's going to be constant acceleration. So I'm specifically looking in the y direction. Now, point B is characterized by zero velocity in the y direction. So the velocity in the y direction equals the initial velocity. This is the initial velocity in the y direction squared. And then minus 2gh. The acceleration here again is negative g. And so the acceleration, I'm going to put the minus sign in by hand and then put the factor of g into that formula. Since the whole thing equals 0, and since the whole thing equals 0, this can be solved for h readily. V naught squared sine squared theta over 2g. Here I am plugging the numbers in, 35 meters per second. So the ball was hit at 70 miles an hour or something. The ball comes off the bat, and it's at the A's game, and the fans are wildly cheering when the ball gets launched, thinking, hey, it's a home run. And so the height that this reaches works out to be 25.8 meters, but remember, the ball started off with that 1 meter height above the ground. So you can see how there's a little flexibility here with the coordinate systems. And we've been doing that in the examples in lectures, and you guys have been encouraged to remember that you can kind of take charge with how the coordinate systems are going to be set up. And you can use that to make the problem easier. So in this case, I just set everything at the level of A and C, thinking of this 1 meter above the ground as where my x-axis is. And then on the problems, I just have to remember to put that 1 meter back in. So here it is, putting the 1 meter back in. I said h prime is all the way to the ground, h is within my coordinate system. That worked out to be 26.8 meters. Okay, so, you know, 80, 90 feet in the air, 26.8 meters. Now, in part B, it says, ooh, is it a home run? Is this baseball going to go over the fence, into the center field stands? So there's a fence 120 meters out, and that fence is 5 meters high. So we can do this. What we can say is, since we know how fast this thing is moving in the horizontal direction, at what rate is it making its way in the x direction, we can say that its x coordinate, as it follows this, you know, parabolic path, its x direction is going to be given by v naught cosine theta times t. Now, that enables me to go in and solve for t when x is equal to 120 meters. So I'm going to go out to the location where that fence is, 120 meters away, and divide through by the x velocity, and it says it's going to take 4.46 seconds to get there. Now, why am I interested in getting the time? And that's because what we've talked about with projectile motion is that I've got all these formulas in terms of x, I got all these formulas in terms of y. T, time, is the variable that shows up in both the x and the y directions. So typically we're using time as a way to go back and forth, saying when this is happening in the x direction, at that time, what's going on in the y direction. So we've used the x direction to determine, you know, at the 120 meter mark, 4.46 seconds have gone by, and now I'm going to take that 4.46 seconds and plug it into my y formula. Now the y formula says, the y formula, putting all the numbers in, says that the y value works out to be 3.5 meters. Okay, now 3.5 meters, that's saying that the y coordinate here is going to be the 3.5 meters. Well, the fence is 5 meters high, but wait a minute. Because of that 1 meter difference in our coordinate, and I should have added that into the solution, because of that 1 meter difference here, I have to add a meter onto this. So we're actually 4.50 meters. That's still not high enough. All right. I think I did forget about that 1 meter down here, so that's one of those dangerous coordinate shifts that I did. Oh, I got the 1 meter in. Never mind. I'm sorry. I did get the 1 meter in place. There it is. Why not? So I have shifted the coordinate system back down so that it's at field level, and I put the 1 meter in. So 3.50, that's it, above the ground. No home run for the A's on that one. All right, questions on that problem? Let's move on. So let's move on and take a look at problem 3. So problem 3 here says we have a 70 kilogram person standing on some scales. They took some bathroom scales, they got into an elevator. The elevator is 2,200 kilograms. There's a tension of 18,000 newtons currently in the cable. So we're told that the elevator's going up. We have a measurement of the tension in the cable, and the tension's at 18,000 newtons. It says draw a free body diagram for the elevator with all the forces. What is the acceleration, and what would the scale be reading inside? So here it is. It's not a difficult free body diagram. There's the elevator. Now I'm just going to say for part A, I'm going to combine the elevator and the person, and it says draw a free body diagram for the elevator. So yeah, I'm just going to combine the person in there too. I guess I could have put a normal force from the person pushing down. That might have been a good way to show the person individually. But I added the person's mass on and said that combined elevator plus person, there's an mg force, 22,250 newtons. Now the tension is only 18,000 newtons. So if that's the case, if t is less than mg, it must be the acceleration is downwards. It must be that this elevator is moving upwards, but that it's slowing down. So the elevator is going upwards, that's what they told us, but the elevator is slowing down. It's been going at a faster speed, and now it's going to drop down and not be traveling as fast. So the acceleration can be calculated, as always, by looking at the force diagram, identifying the net force in the direction that we've designated for the acceleration. Now, again, I'm going to pick acceleration to be downwards, and so mg is in the direction of the acceleration. T is opposing the acceleration, that gets a minus sign, and then divide through by the inertia. And that's a pretty good acceleration. So 1.87 meters per second in the downwards direction. Now, let's see what we've got here. So we got the diagram with the forces. We got the acceleration of the elevator. What does the scale read? So now we've got to shift our focus. Instead of looking at the elevator and the person as one object, now we got to focus in on the person. So here's the person. Those are some really big bathroom scales. So here's the person, here are the scales. What's happening with the person is they're going to have the same acceleration as what we just calculated. So it's not just the elevator that has this acceleration. The person inside has the very same acceleration. Now, from the diagram here, we're going to get that the acceleration is equal to mg minus n. So this is a normal contact force. And so mg minus n divided through by the inertia. So mg gets the plus sign because it's in the direction of the acceleration. N gets the minus sign because it's opposite the direction of the acceleration. And solving, now the person is 70 kilograms, it says, and I'm going to plug in n is equal to m, I'm going to solve, n is equal to mg minus ma, a little bit of algebra on this. And it says that the normal force then is going to be 70 kilograms, common factor of mass, and then this is the gravitational field minus the acceleration. So it says the normal force, which is what the scale is going to be reading. The scale will be pushed downwards with normal force of n, and so that force is going to be 555 newtons, and that says that the effectively the mass that we're going to be reading on that scale is n divided by g. So I can take the 555 newtons and divide by the gravitational field. Now, when I say m prime here, what we're talking about is what would the scale read? And the scale would read 56.6 kilograms. So the scale is going to read something less because of that acceleration that's taking place. All right. So the scale is going to be reading a reduced normal force, and that's going to show up in terms of kilograms. All right, any questions on that? All right, let's take a look at this last example on this first set of problems. So that problem maybe also, no, it's pretty it's pitched at a pretty good level. We could have added another question on that one. Anyway, let's move on to the last one. So here it says that we have two blocks. They're both on inclines. So yeah, you want to make sure that you can do problems with objects on inclines. Inclines are an important part of what we looked at in chapter 4. So we've got the two blocks. They're connected with some kind of a string, and they're sliding. They're not, 7 kilograms and 3 kilograms. Those are pretty good sized blocks. I hope the string is sturdy. They're sliding along frictionless inclines. Now, friction comes in chapter 5. So right now, nothing here includes friction. But it says draw force diagrams, free body diagrams, for each of the blocks. And then find the acceleration, find the tension in the string. So let's do that. So here are the force diagrams. So for each one of these blocks, I think I'm calling the mass here M1 on this side and M2 on the other. For each of these blocks, what I've done is I've taken the gravitational field and I've already divided it. So I feel like we've been through enough of these examples now. If you're still not sure about how the gravitational field divides up into sine and cosine factors, go back and review some of the lectures that we've done with that. So I'm at this point I'm just going to be putting in m1g cosine theta 1, m1g sine theta 1. Oh, that does have a 1 on it right there. And then sine and cosine components for m2g. Now theta 1 is defined relative to the horizontal axis and or the horizontal, and theta 2 the same. So the reason we're getting the sines and cosines dividing up, we've defined the incline angles in a standard manner that we've done, where theta 1 and theta 2s are measured relative to the horizontal. And then the tensions. Now, the tensions on both sides are going to be the same. Until we get to chapter 10 and 11 and start looking at more detailed with rotating objects. Up until then, we are going to treat the pulleys, whatever we have that's rotating, as being a negligible effect, saying that their mass doesn't affect the motion of these two blocks. So, in fact, I made the pulley really small, intending it to be massless, I guess. In any case, the tensions on each side are going to be the same. The normal forces will be different, N1 and N2. So we've got the normal forces, we've got the gravitational force, and we've already divided those into components. And then the tensions. Now, there's no frictional forces, so at least for now, in chapter 5, we're going to bring those in. So on the left, we can say that block number 1 has an acceleration. Now, I picked up the incline to the right and then down the incline to the right. I picked a direction. I didn't really know, looking at the diagram for sure. This block has the advantage that it's heavier. There's going to be a larger gravitational force acting on the 7 kilograms compared with the 3, but it's not as steep, right? So what we're kind of comparing here to decide, which direction will this thing accelerate? It depends on these two forces. It depends on m2g sine theta 2. That force specifically is going to be pulling it down the incline to the right. But there's an opposing force, m1g sine theta 1, trying to pull it in the opposite direction. And whoever is bigger is going to determine the direction of the acceleration. Right? Okay. So, and again, this is the way that you approach these problems. You talk, you're in a study group talking about them, or you just stop on your own studying, and you're kind of reminding yourself, talking yourself through these problems. All right, so let's see what happens. I guessed going to the right. So if I look at the block number 1, in the direction I've designated as my acceleration direction, I do have a force of T, but then I have a gravitational component opposing the direction of the acceleration, and then the whole thing gets divided through by the inertia, m1. For the block on the right, the acceleration formula would be, here's my net force. I have a force of m2g sine theta 2 in the direction of the acceleration, and on this side, tension is opposing the acceleration, so that gets the minus sign, and then divide through by how much inertia. Now, I took those two equations for the acceleration, and it's important here to realize the accelerations are going to be the same. because there is a string attaching these two blocks, and whatever the acceleration is for the block on the right, it's going to be the same for the block on the left. So I don't have two different accelerations, I just have one. So I took the equation for block 1 and solved for the tension. This is how large the tension would be in terms of, algebraic expression. And then for the block on the right, block 2, this is my tension formula. Now what that gives me is this. I can take these two expressions and set them equal to each other. That would enable me to go through and calculate the acceleration. I could also work from those top two formulas. Now, if I set these two expressions equal, I could solve for the tensions. So we're set up here pretty well. So let me take these and set them equal to each other. So t equals this, t equals this. I can set the two thises equal to each other, and then bring all the terms with an acceleration on the left. Everything else goes on the other side. On the left, I end up with an acceleration times m1 plus m2. On the right side, I have my two forces that we said were driving the whole system. And because of the way we carried out the algebra, the tension has been eliminated from the equation. So I had two equations. Up here I had two equations, two unknowns. Now I have one equation, one unknown. And the acceleration then is given by this expression. And I always want to pause at that point and say, look, in the numerator, those are the forces that are actually, for the entire system, determining what the net force is, and then how much inertia do we have. So in the numerator, this is the net force driving the system. In the denominator, we have the net inertia reducing the acceleration of the system. So both objects contribute to the inertia, and then these two gravitational forces are opposing each other. I now writing down all these numbers, putting them in. I ended up with a pretty small acceleration. It is to the right. So at least if I've gotten the numbers correct here, that's 7 kilograms, but the smaller angle wins out very slightly over the 3 kilograms with the larger angle, so that there's a very slight acceleration to the right, 0.647. Now, in part C, I want to come back and solve for the tension. And so I could come back to these two equations, eliminate A and solve for tension here. That's a good approach. Or I could come down to these two and solve for the tension from one of these or for both of them. And for me, it's kind of a coin toss as to which approach. I do want to be able to check my answers. And so I thought when I was doing this solution, if I solve this and I solve this, then I can look to see if the two numbers match. If they match, that's an indication I may have done the problem right. It's no guarantee, but it at least shows consistency at some level. If they don't match, then I've done something wrong. So I carried out each one of these tension calculations. So again, there's only one value of tension. And since both formulas gave me that same value and it matches, that's an indication that we might have done the problem correctly. Now, I could go back and do some other checks, but I'm going to move on to the next. I guess that's the end of the problem here. So there you go. There's an example of, a midterm. There's an example of a midterm from some number of years back that was given, and it's got a couple problems that are a little easier, and it's got a couple problems that are a little more challenging. But that's, I think that's a fair representation of kind of the difficulty. Now I know that what happens is students, whenever you guys take the actual midterm, I know that the actual midterm always feels more difficult than some of these practice ones. In any case, if you guys want to take a break now, you can just pause this. I'm just going to jump into the next set of problems, so here I go. So here's another midterm from, I didn't go back and see how far back these are from, but again, what I've got is 4 problems. Individual problems have A, B, C, D stuff kind of going on, and some are a little easier, some are a little more challenging. Anyway, this is the very same format, and that's what you can expect for our midterm 1 that is coming up. So on this one, again, this is roughly speaking, this is chapter 2, chapter 3, and then a couple problems from chapter 4. So if there's only one chapter you have time to study in preparation for the exam, well, look at them all, but chapter 4 is going to have probably more coverage. Let's see. It says that we have a couple stones at the top of a high cliff. We drop one, and then we wait exactly 2 seconds, and then we throw one downwards at 40 meters per second. Now, 40 meters per second, that's that's like 90 miles an hour or something, right? That's like a major league pitcher. So you got to have a good arm to be able to throw it downwards. But the idea is this. Person dropped the first stone, waited exactly 2 seconds, and then they threw the second stone down as fast as they could, and the person was able to get the second stone to catch up with the first one right as they both impact at the bottom. So what we can do is, here's my diagram, here are my velocities, I'm thinking in terms of how much time for each. So h is equal to 1/2 gt squared for each one of the, for the first one, because it was dropped from rest. For the second one, this got an initial velocity, so I'm going to add that extra term in. Now, I'm treating the top, where we drop these or threw them, as being the 0 point, x equals 0, or height equals 0 here, and then h is increasing on the way down. Okay, this is the way I'm treating it, I guess. Now, T1 is equal to, the first stone got 2 extra seconds of time. So T1 is equal to T2 plus an additional 2 seconds, and then I wrote down the V0 is 40 meters per second. All right. So what I did then is I took these 2 expressions for h and set them equal to each other. For object 1, I got 1/2 g. Now T1, I'm writing as T2 plus delta T squared. And then here, well, it's already T2 squared and T2. So I wrote those 2 expressions down. I multiplied this one out. So I got 1/2 gt squared, T2 squared plus GT2. Yeah, that's got an extra factor of 2 in it. So I multiplied that out. And then what happened was, now I played around with this a bit to get this to work, but what I found was taking this approach, I could get the squared terms to go away. Now, why is it important that the squared terms go away? Because I don't want to do a quadratic unless I have to. I'm capable of doing a quadratic formula, but this approach, the t squareds, the T2 squareds canceled out. The stuff that I'm left with is in terms of, I got a T2 here. The delta T I know, so the delta T is 2 seconds. That's a known value. And then I have a T2 here. So I took this algebraically, I put all the T2s on one side, and I brought everything else to the other side. And then I solved for T2, and I knew all these values. So I could put the numbers in for T2, and I ended up with a T2 value of 0.961 seconds. Okay, so that second stone that got thrown down at that really high speed, it was only in the air for about 1 second. Not quite 1 second. Pretty close, but not quite 1 full second. Well, if that's what T2 is, if this is the value of T2, T1 needs to be larger by 2 seconds. So that became 2.961, and I kept some extra significant figures here to make sure I would not have round-off uncertainties. Once I got the T1s and the T2s solved, then I went back to the original formulas, put those back in, put in the V naught, and again I'm checking my answers. So I'm solving using the first equation, and then I'm solving using the second equation. And they both gave me the same answer. That's a good sign. 43 meters is the distance that these have traveled. So 43 meters is the height of the cliff, something around, I don't know, 90 feet high, something like that. Oh no, higher than that. 120, 30, 40, 150, feet high, something for 140, 150 feet high for the cliff. Now, this algebraic expression, one more item I wanted to point to, this algebraic expression right here, notice that the V naught that I throw with needs to be bigger than G delta T. If that's not the case, then I won't have a positive solution for T2. So that's kind of an interesting algebraic thing. I've only got so much distance to work with. If I throw this object and I don't give it a speed greater than so the first object has dropped for 2 seconds. It's already traveling at a certain speed, and that's what G delta T is saying. It's saying that object 1's already going this fast. I have to throw object 2 faster so that it can catch up. As long as V naught is greater than G delta T, it will catch up. Okay. Anyway, that's just one of the items in the algebra, in the formula we came up with. All right, moving on to problem 2. Problem 2, we've got, so I do want to say this about problem 1. So these kinematics problems can be tricky sometimes. So like on this one and on the first one too, be really careful about setting stuff up and how you've defined formulas. Anyway, let's move on to 2. So here's a projectile motion problem. It's not a baseball going over the fence at the ballpark, but it's a projectile being fired from the edge of a cliff. So what's going to complicate this is I'm starting from a point different from where this thing is going to land. So here it does say draw a diagram. So you need to draw a diagram that actually shows what's going on and label the important points. On part B, it says how long is the projectile in the air, and I pulled out my Y formula. It's really what's going on in the Y direction. It's the gravitational effect that's going to determine how long it's in the air. Since it's going at constant velocity in the X direction, it can just, travel whatever distance it's able to in the X. What's really limiting the time is gravity is bringing this object back down. And so I brought in one of the Y displacement formulas and said we're starting at a height of, now I called this H, 110 meters, and then I put in the initial velocity and the acceleration terms. This did give me a quadratic. So sometimes you just have a quadratic formula. And so I thought this would be a good chance to solve a problem using the quadratic. So first step was to set it up in standard quadratic form. So y is actually equal to 0, that drops out. And then, for me, standard quadratic form is the t squared term, followed by the t term, followed by the constant term. And then I just like to have a positive coefficient on the t squared term. So I wrote it that way and put the minus signs here. Now the t is going to be b minus b over 2a. So that's v naught sine theta over g. And then plus or minus b squared minus 4ac. Now minus 4ac, the minus signs cancel. I'm going to get a plus 2gh. There's the square root over g. Now, this is the way I tend to write the quadratics. Rather than put them over a common denominator, I think we talked about this in lecture, over a common denominator, I separate them because often these terms within the quadratic solution have meaning. This worked out to be, the time is 5.015, I kept an extra sig fig, plus or minus 6.899. Now, the solution we want is at point C, and that is the plus sign, and here's why. So that worked out to be 11.9, and I rounded back 11.9 seconds. The 5.015 seconds here corresponds to how much time did it take to get to point B, the highest point. This is solving for a parabola in terms of time, not the diagram we have, but if we plot this out as a y, as a function of time, we could replace the x-axis here with a time axis. This is how long it takes to get to the top. This is how long it takes to come back down. The plus or minus is saying if I look at the top, that's 5.015 seconds has passed. If I go forward in time, I need to go forward in time an additional 6.9 seconds to get to point C. If I go backwards in time, I need to go backwards in time 6.9 seconds to get to this point where we're back at elevation 0. Now that never happened. So this, as you can see, if I take the minus solution, that gives me negative time. So what that's saying is if I go back before the launch and treat this as if the projectile was following this parabolic path all the way back to here, that's what the negative solution tells me. And that's not, I don't want that one. But again, solving the quadratics this way, two distinct pieces. That first piece, this time it's v naught sine theta over g, it means something. It's that intermediate point in the trajectory. All right, moving on to point D, it says how far downrange has this gone. I get that from v naught cosine theta t. Plugging the numbers in, I hope I got everything right. 60 meters per second, cosine of 55, 11.9 seconds. It says that it's going to land 410 meters out from the base. So if the base point is right here, during that 11.9 seconds, it will have traveled 410 meters downrange. And then finally in part D, it says what are the velocities components when it hits. Now, it's going to hit at some kind of an angle. It will continue to have a Vx all through the problem. And the Vx throughout the problem is v naught cosine theta, because we're ignoring air resistance. And that works out to be 34.4 meters per second. Now, Vy formula would be v naught sine theta minus gt, and that's giving me a negative 67.5. So the numbers seem reasonable. So I'm continuing to move in the positive x direction, 34.4 meters per second, but I'm coming down. So this is 67.5 meters per second in the downwards direction. And if I take those two components and combine them, it says I'm traveling at 75.7 meters per second at impact. And since I'm working locally within one of these quadrants, I have defined theta as being somewhere between 0 and 90. And so when I do the tangent, I'm going to ignore minus signs. I'm going to put the absolute values on Vx and Vy since I'm working within one quadrant, and the theta worked out to be 63 degrees. So everything kind of checks out. I've got the diagrams to help me check and make sure that everything is making sense. Okay. Now, one thing I should mention here too is it says what are the components of the velocity right when, now I used to write the questions this way, right when the projectile impacts. So I would say what's the velocity of the projectile when it hits, and a good number of students would say 0. They thought the idea was once it hits, it's not going anymore, but that's not the idea of these questions. So if you get a question like this that says, what's the speed at impact, or what's the speed when the projectile hits, it's not 0. So it's what's the speed of impact, and that's what we've solved for here. All right, moving on to problem 3. Here's an incline problem on this one too. So almost guaranteed there's going to be something with something with an incline going on in these problems. So, and there's the incline, there's the angle, and again, I guess I needed to for the review, it would have been good to go back and, so I've got an mg force directly downwards. So gravitational force, mg directed downwards, that's going to get divided up into mg sine theta and mg cosine theta components. That's what's going to happen here. And so theta is equal to 0, the mass is equal to 5 kilograms. That's my force diagram. I got the normal force, there's no friction force. So I'm going to say this is a pretty easy problem. It actually needs some additional questions on it. It's a little on the easy side. The force diagrams should be pretty straightforward. The acceleration here is due to mg sine theta. That's the force along the incline. That net force gets divided by the mass, and it says the acceleration of this block, it's independent of the mass. It's given by g sine theta, and that works out to be 4.90 meters per second squared. Now they ask in part C, how fast is it moving after sliding a distance of 4.5? We're assuming it started at rest. So initial velocity is 0 meters per second, distance is 4.5. I get to pull out one of those constant acceleration formulas. This is what's great about the problems from chapter 4. You can do the whole chapters 2, 3, and 4 stuff all combined by having an object with a force diagram, determining the acceleration formulas, plugging some numbers in, and then follow up with some kinematics. So here's one of my formulas for constant acceleration. The v naught is 0. I plug in the values. Don't forget square root sign. Square roots. Square roots get forgotten pretty often. And it turns out that after sliding that distance, we're predicting it's traveling at 6.64 meters per second. So again, any questions on this, let me know. Highly, highly recommend going back and make, if you're clear on this, it's fine. We've emphasized this in class already. Make sure that you understand how the gravitational force components get divided up. Who gets the sine, who gets the cosine, and how to draw the diagrams. All right, last problem here. What we've got is a force, 575 newtons, pushing on 3 objects all lined up. They want to have, first of all, draw force diagrams for each of the crates. So here's what's going on. We're pushing, there's no friction, it's level. There's got to be an acceleration taking place. It's just unavoidable, given that there are no frictional forces opposing force F. So here are the force diagrams. So for each of the 3 blocks, there's going to be a gravitational force down. There's going to be a normal force, N1, N2, N3, and individually, N1 will equal M1G, and N2 will equal M2G, and N3 will equal M3G. Now, there's forces acting between them, and that's what we want to solve for. So I'm calling this normal force N12. Now, normal forces act along vertical surfaces, and that's what we're seeing here. The blocks are pushing against each other, and this is an example of using the third law of motion and saying that when these blocks push against each other, see M2 and M3? They don't directly know about force F. You know, all that M2 knows is that block 1 is pushing it in that direction, and block 3 is pushing it back in this direction. So here's the block in the middle. N12 from this direction, N23 from here, along with the normal and gravitational forces vertically. And then for block 1, it's getting pushed back by block 1 and 2. And so this is your chance to go back and reinforce your conceptual understanding of how does the third law of motion work? How the heck does that work? These 2 forces will be equal in magnitude and exactly opposite in direction. And it's block 1 pushing on block 2, and it's block 2 pushing on block 1. And it answers a very important question of how are these 2 forces related? They're the same magnitude. Same thing with the contact between 2 and 3. All right. Now, in part B, we can come in and say, make sure that your force let me go back to A. Make sure the diagrams are clear, okay? Practice now. When you're doing these problems, practice drawing diagrams that are clear. I always feel like sometimes students draw diagrams that are a little vague because they figure if I draw it kind of vague, then the instructor can't take points off because they won't know if it's right or wrong, but I can take points off. So unless it's really clear about how these forces are arranged, I can take, I can remove points for that. So practice drawing these things clear, and if you don't understand how they work, then go back and understand what these arrows represent. Stop by office hours. Let's look at some examples about how to draw these force diagrams. Drawing the diagrams reliably, that's a really important part of these problems. Now, what I can do at this point is I can play that game of, how many objects do I have? Do I have 3 objects? Or do I just have 1? And I can approach it either way. Since these objects all have the same acceleration, I could combine them as if they're all one object. And that turns out to be an easy approach for part B. Because in part B, I go, okay, I really just have one object. It has a mass of m1 plus m2 plus, it has a mass of 225 kilograms and a force of 575 newtons, and that's it. There are no other forces in the horizontal direction. That's going to give us an acceleration to the right of the one object, 2.56 meters per second squared. Now in part C, it says now go in and calculate the contact forces between the blocks. Now that can't be done until we separate them out individually. So I can't calculate N1, 2 without separating block 1 from block 2 and treating them separately. Same thing with N2, 3. So what I did then is I said, okay, all the accelerations are the same. They're the same as what we just calculated, and they're given by the expression F over M1 plus M2 plus M3. So the acceleration for block 3, now I started with this one because the diagram's a little easier. So as far as block 3 is concerned, it really only has one horizontal force. It's that force providing that acceleration. So the acceleration is provided by N2, 3 divided by just that one block. So that's just M3. And so it says that I need a force of N2 that's equal to M3 times the acceleration. Now I could have solved it right there, and maybe I should have. But instead I decided to push the algebra one more step. I took this expression for the acceleration and substituted it in. What it says is that the contact force, N2, 3, between those two blocks is given by M3 over M1 plus M2 plus M3 times F. You're going, oh, those contact forces are gonna depend on how much mass specifically M2 has in comparison with the entire 3 blocks. So N2 will be some proportion of F, and the proportion's given by this. So N2, it's 15.6%, it's 0.156 of F. So N2, 3 will be 89.4 newtons. Now for block 2, I did kind of the same thing. Now here, block 2 is a little more complicated. I have an N1, 2 coming this way. I have an N2, 3 going that way. So I put both of those forces in, which I need to do, and then I divided through by the mass of block 2. So that's how the laws of motion work. It's the net force divided by the mass. And for that then, I solved for N1, 2 is equal to N2, 3 plus M2 times A. Now N2, 3 had already been solved algebraically to look like this. So when I took that piece and added on M2A,
Now I could have added a line or two of algebra, but I didn't. I chose not to move on to another page. So check that out and see if the algebra really works. What we can show is that N12 is equal to M2 plus M3 divided by the combined masses. So at this point, I've got 0.644 times F. Now what would happen if and then I got 371 newtons. What would happen if we rearranged the three blocks? If we put them in different order, you know, I moved the 80 and those are big blocks. I moved the 80 kilograms, the 100 kilograms, 10 kilograms, 35 kilograms, I rearranged them. Well, the acceleration is going to be the same in any case, however they are arranged, because it's just the force divided by the net mass. But the individual N12s and N23s will be different, right? Let's see, currently M3 is by far the smallest mass. N3 by itself doesn't need so much force to accelerate, and you can see that N23 is just a fraction of F. But if we took M2 and moved it out to that front, that would need more force. So again, the contact forces between are going to depend on the individual masses, whereas the overall treating it as one object effect says doesn't matter how we arrange them, the overall acceleration will be the same in any arrangement. All right, so there we go. That's a chance to go in and see what another midterm looks like. I hope this went well. You know, if you're staying caught up in the course, these should all, at the very least, look very, very familiar. You should be able to look at the problems and immediately start working on them, getting the diagrams drawn and such. So we're definitely in, you know, prep mode for midterm 1. So got plenty of office hours out there. Stop by. Whatever questions you guys have, we will get those looked at.